our today's discussion is based upon this binomial distribution and Poisson distribution. Both of these variables are discrete random variables, and uh, we shall discuss the structure of these variables and their probability mass function as well. Now, let us begin with a problem. Okay. I have named the problem as a digital channel problem. Now, this problem states that all of you, if you have copies in front of you, you can note it down. The problem states that the chance that a bit transmitted through a digital transmission channel is received in error is 0.1. Also assume that the transmission trials are independent. Let capital X the number of bits in error in the next 4 bits transmitted. Determine probability of X equal to 2. Determine probability of X equal to 2. Now, you see, here we are talking about the number of bits received through a digital transmission channel. And the bits can be received in 2 ways. Either the bits are correct or the bits are wrong. Okay, if the bits are wrong, that means you are receiving the bits with some error. The probability of that is given to be 0.1. Now the trials, how many trials are there? 4 trials are there, because your system is receiving the bits successively 4 times consecutively. So 4 trials are there. Each of these trials are independent of one another. This means if one bit is being received, it is not affecting the quality of the other bits. So they are independent of one another. The bits are independent of one another. Okay, so trials are independent of one another. So in this way, your digital transmission channel is receiving the bits. But here we are interested in those bits which are received with some errors. Okay, these are not the actual bits. Some errors are there. Why am I so much interested about these bits with error? Is because we want to extract out those bits, and we want to what should I say, modify them, or we want to keep those unwanted bits aside. Okay, now that's why the receiving of the bits in error, these are success to me. Let capital X be the number of bits in error, in the next 4 bits transmitted. Okay, what I am supposed to find what is the probability of 2 bits which are in error. So probability of X is equal to 2 is the item which I am supposed to find right now. Let us try to solve this problem together. Let the letter capital E denote a bit in error, and let the letter capital O denote that the bit is okay. That is, okay means the bit has been received without error. We can represent the outcomes of this experiment as a list of 4 letters that indicate the bits that are in error and those that are okay. So here we have listed 2 to the power 4 means 16 possible outcomes, where 4 consecutive bits have been represented for each of these outcomes. And you see, so for example, if we consider the first outcome, here all the bits are in okay position, means all the bits have been received without error. And if I consider the last outcome, all the bits have been received with some error. So here there are in total 16 possibilities. So all these possibilities have been considered. Now, according to the problem, we are interested about counting the number of bits those have been received with some error on. So we are only interested about the error bits. So here we are going to define the random variable with number of bits with errors, and therefore I have considered this small x over here. This small x counts how many bits are in error in each of these outcomes. So for the first outcome, the number of bits in error is 0. For the second outcome, the number of bits in error is 1. For the third outcome, the number of bits in error is 1, and so on. Here, for EO, the number of bits in error is 2. Here, the number of bits in error for EEO is 3, and so on. And lastly, the number of bits in error for the last outcome is 4. So all the values of the random variable have been obtained. How many distinct values are there for the random variables? 4 distinct variables are there for the 4 distinct values are there for the random variables. These are 0, 1, 2, 3, 4. So we already know from our previous class the random variable is a function where the domain is the set of all possible outcomes, and the range is the subset of set of real numbers. This column and that column represents your domain, and this column and that column represents your range. So range contains the numbers 0, 1, 2, 3, 4. So this is the subset of set of real numbers. Now, we are interested about the event where capital X equals to 2. Now, remember, event is not an element. Event is a set. Event is a subset of the sample space. What is the definition of event? Always say that event is the subset of the sample space. My sample space consists of 16 elements. So here I have considered only those. In this particular set, I have considered only those consecutive bits where only 2 errors are there, 2 error bits are there. And the number of elements present in the event capital A is 6. Under the assumption that the trials are independent, if we want to find the probability of one of these bits, say double or double E, then its probability is calculated in this way. The probability of double or double E is probability of O into probability of O into probability of E into probability of E. Now, let us go back to the question once again. In question, it is mentioned that the number of bits received with error is, the probability of that is 0.1. And O represents the bits are okay, E represents the bits are in error. So keeping these in mind, the probability of O will be 1 minus 0.1, and probability of E will be 0.1. So I have substituted all the probabilities over here. I have multiplied, and the probability has come out to be 0.0081. I hope you have understood the problem. Okay. Now, probability 0.0081 is the probability of one such sequence of bits. Now, how many bits are there in our the event which we are concerned with, that is capital A? In this event, there are in total six possible sequences are there. So the number, if I'm interested about the number of 2 error bits or 2 error bits, then probability of X equal to 2 corresponds to either of this outcome or 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 this outcome. So these are the possible outcomes which can happen in mutually exclusive ways. So we know that if capital A and capital B are the outcomes which are mutually exclusive, then in that case probability of A union B will be equals to PA plus B. So I have applied this formula over here once again, and since we have calculated the probability of double or double E to be 0.001, see, since in each of these outcomes only 2 error bits are present, each of their probabilities will be 0.0081, and since there are 6 possibilities, so 0.0081 has been multiplied by 6, and hence we have got the probability 0.0486. I hope you have understood how I calculated this particular problem. So I have considered so many things over here. I considered the chart, and we considered the event, and after applying the theorem of independent probabilities, ultimately we are able to find out the probability of 2 error bits, which is 0.048. We shall now try to solve the same problem from a different perspective. The perspective is already known to you. I have discussed it in the last class, but again, I'm going to discuss it today. because my today's discussion is mainly based on this particular topic. So for the same problem of bits, let us see what information we have with us right now. Now, given n equals to 4, because we are considering the 4 consecutive outcomes, 4 consecutive bits are received. So my n is equal to 4. My success is, I will achieve a success when I will capture a bit with some error, according to the question. So my probability of success is 0.1. And so by the binomial probability law, the probability of 2 successes will be probability of x equal to 2, 4c2, 0.1 to the power 2, 1 minus 0.1, whole thing to the power 4 minus 2. Again, it has been calculated as 0.0486. Now you see, if this particular problem where I considered so many things and it took me some time to tabulate all the outcomes and calculate the probabilities, it was a matter of seconds if I solved the problem with binomial probability law. Okay, it's a matter of 3 lines only. Binomial probability law can solve the problem very easily. Okay, you don't have to tabulate anything at all. Now, the question is, the important question is, when we shall be able to apply the binomial probability law? What are the conditions under which binomial probability laws are valid? How shall I judge a particular system and tell that the binomial probability law is suitable to the system? Because if a certain probability law is not suitable to the system, it becomes meaningless when we apply the system, the law to the particular system. You will understand. I have an example with me. After I finish this particular part, then I'll go to that particular example where I shall tell you what happens when a wrong probability law is applied to a wrong system. Okay, the probability law and the system should match with each other. Now, what are the conditions by which we judge that a system is suitable for binomial probability law? Is that your trials must be Bernoulli trials. Now, what are the Bernoulli trials? Bernoulli trials are those trials where there are 2 types of outcomes. One is success, another is failure. Or you can say Bernoulli trial is a kind of trial where the success is where 2 outcomes are there. One is 0 and another is 1. So first of all, the outcomes must be Bernoulli. The trials must be Bernoulli. Trials must be independent. Each trial result in 2 possible outcomes. And probability of success in each trial must be known and should be constant throughout the experiment. Okay. Now, if these are the cases, then under these assumptions, the binomial probability law is defined as this. Yes, in last class also I defined this formula. The formula is given to be NCX, p to the power x, 1 minus p whole thing to the power x. And x takes the values 0, 1 to up to n. These are the values, possible values for x. P lies between 0 and 1 because it is probability. Now, this is called the binomial probability law, and the random variable is said to follow the binomial distribution. Now, if I go back to the digital channel problem once again, you see all these characteristics are satisfied over here. First characteristic was the trials must be Bernoulli. My trials were Bernoulli because either I was receiving the bit with error or bit without error. So that trial was actually a Bernoulli trial. Secondly, we considered 4 consecutive bits, sequence of bits. So my number of experiment here is 4. So n is known. Success was to get some bit with some error. That is the success. And probability of success was also known. That is 0.1. So all the trials are independent, as mentioned in the question. All the conditions of binomial probability law, all the conditions suitable to binomial probability law were actually applicable to the digital channel problem. So we could solve the digital channel problem by binomial probability. Okay. So that's how we judge whether a particular probability law is suitable to a particular channel or not, particular system or not. One important result for binomial distribution is that if capital X is a binomial variable, its mean is NP, and its variance is calculated as NP into 1 minus P. These are two important theorems. Okay. Now, in previous years, we have often seen that the proof of these theorems used to come. But nowadays, the way of studying mm, studying has changed in Macaus. So Macaus has become more and more application based. So you will expect problems with applications, application oriented problems. Okay, in the examination, probably the proof of this theorem will not come, but the application of this theorem may come in the examination. But since connected suddenly, extremely sorry, just a minute, just a minute. Hope you are able to see my screen. Um, Now, all of you, I'm requesting, I saved your chat, but I'm requesting once again to all of you to write your roll numbers in the chat box. Okay. Anyways, so binomial probability law is actually the mean of the binomial variable is given to be NP, and the variance of the binomial variable is NP into 1 minus P. I shall, since this results, the theorem of the proof of this formula used to come in the examination, I shall prepare a note on that and I will post it in Google Classroom so that you can study at home. Okay, but most of the time, most of the cases, we shall be dealing with application-oriented problems. Let us discuss another problem. A multiple choice examination has 3 possible answers for each of 5 questions. What is the probability that a student will get 4 or more correct answers just by guessing? Now, let us judge whether binomial probability law is applicable to this problem or not. You see that the trials here will be independent of one another. Okay, the trials are actually defined by students attempting a particular question. He can attempt it independently. Okay, he can simultaneously attempt all the questions. The attempts are independent of one another. So trials are independent. How many questions he is supposed to attempt? The number of questions is 5. So n is known. What is success here? Success is to get a correct answer, correct option from all the possible options. How many possible options are given? 3 possible answers are given. And since student doesn't know the answer, he has to guess the answer. So he is bound to select the options with equal probability. So probability of success here is 1/3. So all the information about small n and small p are known. Remember one thing in binomial probability law. In binomial probability law, the number of experiment small n and probability of success small p, they are actually parameters of the distribution. If the parameters are known, your distribution is known. So how many parameters are there for binomial law? 2 parameters. One is small n, number of experiment, another is small p, probability of success. So here in this problem, both the parameters are present. Small n is equal to 5, small p is equal to 1/3. We are going to find the probability that the student will get 4 or more correct answers, which is denoted by probability of x greater than or equal to 4. But by binomial probability law, we know that probability of x equal to small x, that means the student will get small x correct answers, is given by this probability. Okay, this is the probability. And so therefore, if I substitute now probability of x greater than equal to 4 means 2 cases only. Either probability either x is equal to 4 or x is equal to 5, and they are mutually exclusive. So probability of x greater than or equal to 4 means the sum of these 2 probabilities. Now in the formula, I am putting the values 4 and 5 individually, and we are getting the probability to be 0.045267. This is the probability obtained by binomial probability law for the given problem. Let us solve the problem in a different way. And let's see what happens. Now you see, here in this problem of multiple choice question, the number of experiment is small n equals to 5 and probability of success is 1/3. So that their product NP is equal to 5 into 1/3, which is 1.667. Now, the probability that the student will get 4 or more answers will be probability of x greater than or equal to 4 is equal to P of x equal to 4 plus P of x equal to 5. I am going to apply a new formula over here. I shall talk about the formula in details in today's class. What is this new formula? The new formula is probability of x equal to small x, e to the power minus np, np to the power x by x factorial. Here x will run from 0, 1 to up to infinity. What is this formula? I shall come to this point. Okay. Now, if I'm given this formula, see in this particular formula, e is the exponent, which will be automatically known to us if small n and small p are known. Small n and small p are known for the given problem. So we are thinking that all the parameters are known. So probably this formula is applicable to the given system. So without thinking much, to the given formula, I am going to apply all the values present in the problem. Okay, what do I get? Let us see. So here, probability of x greater than or equal to 4 will give you the sum total of these two probabilities. Now, we are substituting one, from our previous case that probability of x greater than or equal to 4 means px4 plus px5. So I am substituting the value x equal to 4 over here for the first case and x equal to 5 over here for the second case. Now, NP has been calculated as 1.667 already. So I'm putting all the values in the new formula, which I have got, and the calculated probability is 0.081. Now, all of us are in a confused state of mind to what has happened. We know binomial probability law, and the teacher has taught us that if the parameters are known to us, then the law can be applied to a particular system. Teacher has also provided us another formula where it seems as if all the criteria are being matched, and we applied the formula, but two different results. One is 0.081 and another is 0.045267. What does it mean? 0.045267 means 4.5% and 0.081 means 8.1%. Means this formula is saying if you take the examination of the student 100 times, he is going to get 4 or more correct answers 8 out of 100, 8 times out of 100 times. And binomial probability law says that if you are going to repeat the examination of the student 100 times, he is going to get 4 or more correct answers 4 times out of 100. What to believe? Which one is correct? All the parameters are known, everything is known. The formula seems to be suitable to the system. But what is the mistake? Now, let's come to this particular point. Okay. So I'm going to get rid of this dilemma. The law which I have considered over here is called the Poisson law. It is not Poisson law. Poisson was somebody's name. He gave the law. And law, you see, the formula is given as probability of x equal to small x, e to the power minus lambda, lambda to the power x by x factorial, where x runs from 0, 1 to up to infinity. Now, when this particular law will be applicable, what are the conditions? The conditions are, in binomial probability law, the small n, the number of experiment, if it tends to infinity, and if the corresponding probability of success is success tends to 0, together if they hold, and if the product of these two items NP is not is significant, means it is considerable, then the binomial probability law tends to follow Poisson. What do you mean by n tends to infinity and p tends to 0? We cannot consider these two items separately. We have to consider them together, pairwise. Now, pairwise, n tends to infinity and p tends to 0. This condition means that I do not know how many times must I repeat my experiment to get the first probability of success. So probability of success for this type of experiment is so poor, so poor. If such is the case, then probability, the Poisson law is applicable, otherwise not. Now think of the situation where students gave the MCQ type of examination. Okay, let us go back to the problem. That was the problem. Here, number of experiment was 5 because he attempted 5 questions, and probability of success was 1/3. Neither 5 is a number near to infinity, nor 1/3 is a number near to 0. Okay, so the conditions written over here were not fulfilled for the given MCQ type of problems. Okay, so not only the parameters, but also we have to judge whether the conditions of the distributions are being satisfied or not. If the conditions of the distributions are not being satisfied, but parameters are known, then that particular probability law will not be applicable. Therefore, when we applied the probability law, Poisson probability law to the MCQ type of problem, that was wrong. I did a mistake because although the parameters were known to me, the conditions were not being satisfied. N was not tending to infinity, P was not tending to 0. So therefore the answer 0.081, although it is mathematically all right, calculation is not wrong, mathematical answer is all right, but physically it has no meaning. So this type of results obtained from statistics after the application, wrong application, are called garbage results. Okay, and they often mislead all of us. So we have to take care of this kind of problems. Okay, we have to be very careful before we apply something to some system. So binomial reprobability law was actually suitable to the given case. There is another form of the Poisson law. It is also sometimes written in this way. If we divide the entire interval, if we denote the entire interval by capital T, and delta T is a very small amount of time, and if delta T tends to 0, then probability of one event in each sub-interval tends to lambda into delta T. It is a condition. And under this condition, the Poisson law can also be written as, the Poisson law can also be written in this way, that fx equal to e to the power minus lambda capital T, lambda into capital T whole thing to the power x by x factorial. Okay, that is another form of Poisson law. In ECE, you have a signal systems, signal processing. Here, Poisson law are always applied. Okay, so you give some considerable amount of time to study Poisson law and binomial law. Okay, so this is actually used as a tool in signal systems. Now here is a problem for you: magnetic storage and contamination. Contamination is a problem in the manufacturing of magnetic storage disks. Assume that the number of particles of contamination that occur on a disk surface has Poisson distribution, and the average number of particles per square centimeter of media surface is 0.1. The area of a disk under study is 100 square centimeters. Determine the probability that 12 particles occur in the area of a disk under study. The probability that 0 particle occur in the area of the disk under study, and probability that 12 or fewer particles occur in the area of the disk under study. So it is already mentioned that the system follows Poisson distribution. So we are in a safe side. We can use the Poisson law. Okay. Now to solve this particular problem, we shall proceed in this way. Okay, let capital X denote the number of particles in the area of a disk under study. Here the mean number of particles per centimeter squared is lambda equals to 0.1. Capital T is 100 centimeters square, total area, and lambda into capital T is therefore 10. So to find the probability that 12 particles occur in the area of a disk under study, it will be calculated by the formula, and we substitute in place of small x 12. So probability of x equal to 12, it gives you this probability. If we are interested about the probability, finding the probability that 0 particle occur in the area of the disk under study, then the probability is calculated here. And if we are interested about to calculate the probability of 12 or fewer particles in the area of the disk under study, it means probability of x less than or equal to 12, and we have to put consecutively all the possible values of small x from 0 up to 12. And if you sum them together, this probability will come. I have given a problem here to you so that you can try it at home. And first of all, you will judge this particular problem and you will satisfy yourself that you are going to apply which particular probability law to the given system, whether binomial probability law or Poisson probability. Judging the system is very important for us. Okay. And also one thing I forgot to mention, that remember, Poisson distribution is a such type of discrete probability distribution where mean of the distribution and variance of the mean of the variable and variance of the variable, they are same. So if I ask you, give us a name of a distribution where mean and variance are same, and discrete, I'm talking about discrete case, then such a distribution is known as Poisson distribution. Okay. And what is the parameter of the distribution? The parameter of the distribution is lambda. So if lambda is known, our distribution is known. So in the magnetic storage problem, lambda was known to us, so we could solve the problem. So we are almost done with our today's class. Hope you have understood. I'm going to upload the video in the YouTube, and I'm going to upload this particular note in the Google Classroom. You go through my lectures once again, and if you have any difficulties, you can contact me. See you next week. Till then, tata, and stay healthy and stay safe.
Thank you, sir.
Yeah.
Thank you, sir.